All right, so welcome back to the NLP class, and hope you guys enjoyed the assignments. And I think you guys are working on A4, right? How is it? Quite easy, right? Right? Not so much, right? I think, but I think you guys agree, right? That SpaCy is quite useful, right? Right? SpaCy is very useful, and I think it's some tool that you guys all should know, right? So today we're gonna uh, learn the same slide that we have, but I think we already learned BERT, and actually we already learned GPT, right? There are a couple of models that we can further learn together. So let us review very quickly. So pre-training is about training the whole model, right? Which also capture the task knowledge. That is like the main thesis of pre-training. And there are two ways in which we can do pre-training. First is language modeling, and second one is a mass language modeling. Language modeling is used in GPT and mostly used in decoder structure. Mass language modeling is used in mostly encoder structure. And based on what I have said, pre-training can be categorized into three categories. Decoder only, in which because it's only a decoder, the only way you can pre-train it is using LM. And what if we want to pre-train using mass language modeling? We have to pre-train it as an encoder structure. And lastly, if we another way that we can pre-train using LM is using encoder decoder structure. So in a language modeling, we want to predict the next token. So if we try to train as an encoder, it does not work very well, right? Because encoder just look like it just, this is the definition of encoder, right? In which it does not have any output in each of their cell, right? So encoder would not be able to predict the next token. So what makes sense is that we should use something called decoder architecture, right? And decoder architecture is nothing but just in every cell, it actually predicts something, right? And by the way, I say that every cell predicts something is basically passed through the H1 to the linear layer, and we got some word, right? Word 1. And this is a H2 linear, and W2, and H3 linear, and W3, right? And this is also H3, right? So that's why if you want to train using language modeling, the only way you can do it is using a decoder structure. Another way you can actually train using a language modeling structure is using encoder-decoder, right? So, for example, by the way, this can be Chucky is eating, all right? So in an encoder-decoder structure, there are so many ways you can actually do this. So you can do something like, right, in which the input could be Chucky is flying, right? So we can imagine that they are basically some sentence that we want to understand, and we call this whole thing encoder, right? And we can also pass this last H to a decoder, in which it can try to predict what would be the next sentence, right? Here, oh, sorry. Right. So this is called the encoder architecture. We can pre-train like this, right? And let it try to predict what would be this token. And this is definitely on his Bloom EOS, right? So in an encoder decoder architecture, you can also train like this, right? In which you train in such a way that the encoder try to encapsulate some information, and then finally the decoder try to predict the next token, right? And this is the two ways you can predict, you can pre-train using language model. So you may have a one very natural question. If both can be pre-trained using LM, then how do I choose, and why do we even need to have two ways? It's all mainly based on the task you want to apply, or the task you want to fine tune, right? If the task that you want to use is use encoder decoder, then you need to pre-train like this, because this is the only way that task can be adapted to. For example, for summarization, if you know that this model will be pre-trained and then it will be eventually used for summarization, then you should pre-train like this. You cannot pre-train like this, correct? If you know that you're going to use this architecture for summarization, for paraphrasing, for machine translation, right? So in other words, saying whether which architecture to pre-train depends on the task you want to adapt to, or the task that you want to fine tune. If you know that your final task is like this, you must pre-train using this way, right? Oh, maybe I have some tasks like music generation, or maybe code generation, or maybe Harry Potter generation, right? Or maybe instruction tuning. Later on, you're gonna study about this, right? We know that all this uh, specific task does not need an encoder decoder architecture, right? For music generation, you just say, you belong to me, and then let it generate the rest, right? Or maybe for code generation, you say import numpy as, and it will generate, right? Harry Potter is, it will generate, right? Or maybe instruction tuning, please translate this sentence. ผมไปกินข้าว and then they will generate the next, right? So you can see that which architecture you use solely depend on the task you want to adapt to, right? But pre-training, make sure that your architecture has some knowledge already, not just blank, not just initialized from scratch, right? So this is like a very, very important things that you must know. Pre-training and fine-tuning, they must like together, right? How about mass language modeling? It is very clear that decoder won't work because in a decoder architecture, you cannot train using mass language modeling because it forces you to always print everything, right? And check everything. And in mass language modeling, we know that we only want to predict certain terms, right? Right. In fact, because in mass language modeling, you only predict certain terms, it may be wise to use the encoder architecture in which you add some linear layer on top, let it predict some of the mass language mass token. But when you actually use it, you remove them. You remove them, right? So that is like the way of thinking why when you pre-train using mass language modeling, you use encoder. Now, you may have one question then. I understand how you pre-train mass language modeling, but what are the tasks that can be adapted using encoder architecture, right? Because here I already say that in encoder decoder, the final task is like this: summarization, paraphrasing, machine translation. For decoder architecture, the final task maybe look like this. I mean, I'm talking about fine tuning. Now in encoder, what would be the task like? And in fact, the only task that it makes sense, actually there are two tasks. One is classification, right? Because in an encoder architecture, you take the last HT for something, right? And then you can take the last HT to pass through a linear layer to classify anything, right? So it makes a lot of sense that in this kind of architecture, it's useful for classification, right? When you fine tune. Another task that I did not write very clearly is a similarity, right? So what does it mean? Well, I can take the HT of one sentence and I can take another HT of another sentence that pass through the same model, and then I can dot product them, right? Right, to check whether these two sentences are actually same, right? So I can actually employ two encoder, try to understand the semantic of these two sentences, and represent by the last HT they have, and then dot product them together, right? So those, when you know that you use these two tasks, it's very natural that you'll use an encoder architecture. And if you don't have a pre-trained model, you should pre-train only this way, all right? So finally, I see so many things. What are the right way to start? So let me kindly delete this, right? So the right way to do is you first need to know what is the task you want to do. In the industry, right? What is the task that you want to do? There are three types of tasks that we already say, right? One is about generation, like purely generation, like music, code, story, right? Or even instruction tuning. Later we're gonna talk. Another one is paraphrasing, machine translation, summarization, and then another one could be like classification and similarity. Actually, there's something called retrieval. Retrieval is basically similarity. For example, you remember the search engine you do in the first class, A1, by using when you get the final embedding, you can search which one is the closest word, right? So similarly, once you get the HT, you can retrieve the similar HT, right? So you can see that that can also be done. So based on that idea, so when you go to your company, which model to use? You should ask this first question. What task you are doing? Oh, I want to generate Harry Potter, you go here. I want to do summarization, you go here. I want to do classification, you go here. Then you need to answer, I already know that I will use decoder architecture. Here you already know you will use encoder decoder architecture. Here you already know you need to use encoder architecture. Then the next step is any model. Any model. When I say any model, I mean any pre-trained model. If yes, fine-tune them. If no, then you need to pre-train them using LM or mass LM. LM, right? This is very true for your language. For example, a lot of you are Thai people, some are from Nepal. So Russia may want to generate music for Nepali, correct? Then she know that she need to do this way. Is there any, then she know that she need to have a decoder. Then she check, is there any pre-trained model for Nepali, right? For Nepali, not for Nepali music. You need to understand. For Nepali, pre-trained means pre-trained model does not need to be task specific. Pre-trained means general. Do we have pre-trained model for Nepali? Okay, maybe yes, then just fine tune it for music. If no, she need to pre-train this whole model using Nepali language. Understood? So this is the way to think. Similarly, here, you need to think the same way. Yes, then fine tune. No pre-trained model, then pre-train using what? LM or mass LM? LM, right? Yep. This one, yes, fine tune. This one, mass. Yep. So these are the structure of way of thinking that you must have when you approach any task in the industry, right? Okay. Anyone has, I will let you guys think for a few minutes. And then once you guys, I'm sorry for the people who already understand a lot, but I have to talk all this to make sure keep everyone are on the same page. Yep. All right. So now, I think there's almost no question in this slide, but if there's one question that you may have is, how do we pre-train? We already know, right? We already know how to pre-train. This one, we already know how to do this, right? But there's one thing you guys don't know is how to fine tune, right? How to fine tune. How to fine tune, right? And in the next couple of slides, actually, we already covered last Wednesday how to fine tune in decoder, right? We already fine, but let us visit that again, right? But again, I will say slowly any questions you guys have regarding this slide. Yes. Both can be used using decoder. So you can imagine. So let me rephrase what Min asked. you are Min, right? Yeah, Min has there are two ways you can actually generate code, right? You can prompt, please write me a code about, please solve this assignment for me, okay? Or import NumPy as, and then it fill the blank, right? Both can be used for decoder structure. You can imagine that, please write this code for me, and then you just keep on letting it fill the next token. Or you can say import NumPy as n, and then it fill. So both can be used in decoder. That's why ChatGPT is so powerful. ChatGPT is decoder only, and it can do basically everything, right? So the decoder is a very, very powerful structure. Can you, by the way, I want to ask you, you asked a very good question. Can I do summarization using decoder? Actually, I can. I can say something like, please summarize this document for me. And then it can fill the rest, right? That's why ChatGPT can also do summarization, even though ChatGPT is decoder. It's not encoder decoder. Can we use mass LM in encoder decoder? Theoretically, yes, right? Yes, right. You can, because there's an encoder, you can ask it to mask at the same time, try to predict the next, right? I can imagine that that is exactly what Bart used, right? By the way, in this area, there's a pre-trained model that is very famous in here, Bart, Pegasus, and T5. Bart used two objectives, mass LM and LM, because decoder can do LM, right? Encoder can also do mass LM. Then this guy called Bart, he used two objectives. So that means that he also asked the model to fill the mass in the encoder, but also asked the model to predict the next token in the decoder. So double objective. Then the model becomes super good. Yeah. But it's possible. Yes. It's not possible. Bart already do it. So you don't have. So that is also a very good question. Can we mix? Yes. And the answer is yes. Okay. I will pause for a few minutes, and you guys can ask. All right. So decoder. So when we pre-train the decoder, there are two ways we can do, right? We can pre-train the decoder as a classifier, or we can pre-train the decoder as a generator, right? So here we can if we want to train it as a classifier, what do I mean by classifier? Well, if you think that your decoder will be adapted to tasks like sentiment analysis, right? Then you should use in this architecture when you pre-train, right? So the way you can pre-train is Chucky is flying on his broom, right? This is the why I always like this, right? And this is pre-training, dueling pre-training, right? But then during fine-tuning, you can just put a linear layer on here and train the linear layer again, right? For a specific task, because this linear layer is not specific to that task, right? So that is the way you can think about how actually decoder as classifier. Here I say that note that the linear layer hasn't been pre-trained, right? Simply because once you pre-train, you need to take this guy out and put a new guy. but you don't change any of the ping, because this ping already captured the knowledge of this sentence, already learned, but you need to replace this linear layer with another linear layer. And then you train only this guy, right? So that this guy learn how to do the classification task you want, right? So that is, what does it mean by that? Any questions? Yeah. Last time my TA told me I'm going too fast, so now I'm very slow. And I try to pause and see your face and then breathe and then try to see whether you guys have any questions. Yeah. Okay. The next one is well, you pre-train the decoder because you know that this decoder will be used for generation tasks in the future, right? Then you need to make sure that this task, this architecture accommodate the future tasks that you want to adapt to, right? In which here you have the linear layer on top. And you can see that when you pre-train the decoder as a generator, all this linear layer is pre-trained, And when you use it, you use like this. You don't take this guy out, right? Because they learn to know how to decode the next token, right? So this architecture can be used right away for generation. Yep. So that's why here I say linear layer has already been pre-trained. Yep. I'm gonna skip the GPT, but you can take a look about this. But in transformer, this is only a decoder structure, right? So in GPT, it's only use a transformer decoder. By the way, if you don't understand this, I will make it very clear. Transformer is the main architecture that we're gonna use, right? And there are three architecture it can be possible. Encoder only, encoder decoder, and decoder only, right? Correct? You need to know the famous model that use this three, right? For the decoder is GPT 1, 2, 3, and Mistral, Llama, right? All of them use this architecture. Decoder only. I did not code this yet in the YouTube. I will code it very soon. Encoder decoder is BERT, mainly BERT. I already code this in the YouTube. Not sure you guys saw that, right? But you will use that anyway because it's A5. A5? Yeah, A5 will be this. Yeah. So A4 is easy, so A5 is a little bit difficult. But no, I don't think it's that difficult like A3. Can anyone tell me the, oh, sorry, it's not encoder. Oh, I made a mistake. Encoder only is BERT. Correct? Yeah. Can anyone tell me famous model that use encoder decoder architecture? But right? But Pegasus. No one is talking about Pegasus anymore. Bye bye. T5 is still. So you need to know this. Yeah, because when you go to Huggingface, you understand that, oh, if I want to do retrieval similarity classification, you should look at this family. If you want to do summarization, blah, 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 paraphrasing machine translation, you need to look at this family. If you're doing like instruction based, like you just want to prompt and then fill the blank, you use decoder architecture, right? Currently, it seems like decoder is winning currently because ChatGPT is very powerful, but you should not like ignore BOT and T5. My students publish ACL using BOT. Yeah. Yeah, I would not talk about this because they are all readable. Yep. So now we we now talk about fine tuning, right? So all of this is classification tasks. So if we train a decoder for generation, and how do we adapt for generation? There's nothing need to be done, right? Just use it and then just train it again, right? But for when you use decoder architecture for classification, the question is how do you arrange the input so that it still can use decoder? Because in some classification tasks like entailment or natural language inference, it comes with 2 sentences, not only 1 sentence, right? Then when you see this, you will quickly say that, oh, Chucky, because there's 2 sentences, I will use encoder decoder, correct? This guy, Radford, say, no, you don't need to use encoder decoder architecture. Just use my architecture decoder, it can work. Simply separate them by a token called delete. And in the program, you just create a token like this, right? Right in the vocab, and that should be. And then he create a token at the end, and then send to the transformer, right? Oh no, actually everything sent to the transformer, but when you pass through the linear layer, you only pass the last token. If you don't see that, let me draw it very nicely for you. So it looks like this, right? So this is the decoder architecture, right? The transformer decoder architecture, right? And here, for example, you have like start, like premise, right? And then you have a delim, and then blah 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 blah, and then you have the last token is extract, correct? And let me just recap you guys' knowledge. In a transformer decoder side, what is the first thing you do? Huh? Yes, but that one is the second part. First part is positional embedding, right? So you add here, right? Add positional embedding for all, and then you duplicate yourself into QKV, right? And Q is basically, so Q is basically the whole sentence, right? Start, delim, extract, right? So this is how the Q looks, right? Yeah, and the Q is sequence length, comma, embedding, because each of them is embedding. And K is the same guy, right? Start, delim, extract, okay? And then you, right, QK, right? Dot them together, right? So when they dot them, then you will know this guy, attention to this guy, how much? This guy, how much, right? Right? How about the next guy? Right? So that is the what do I mean by QKV, right? So you duplicate QKV, and then you do QKV, QK divided by square root of DK, and then time V, right? Here is a little bit strange. In an encoder-decoder architecture, which one come from the encoder in an encoder architecture? Which one come from the encoder? K and V, okay? So in an encoder decoder architecture in your A tree, you can see that K and V come from encoder, right? And Q come from here, right? So why K and V come from here? Because K means that given this thing, what are the attention to K, right? Which is here. And you multiply with V from the encoder because you want to know the attention that you need to pay to here, right? So that is something that you have to be very, if you don't understand what I say, just go back and study and then you understand, right? But anyway, for decoder architecture only, you will see that QKV are the same guy, right? Because there's no encoder, right? So it's basically like self-attention, right? So QKV, QK, you get the attention, right? Get the attention, right? And then when you dot with V, you will know that which one actually is very important, right? Have you ever got? Let me ask anyone in this class who truly already understand what is QKV do. Who in this class truly understand? Or maybe understand like 80%. Okay, one. Okay, then you guys need to learn by yourself how to learn, right? So let me show you, like if I were you and Chucky don't teach, right? Then you will say Chucky don't teach, then you will never understand. It's very simple. You go home, do like this, right? So Chucky is sleeping at AIT. Correct? Yeah. And let's say, so this is sequence length. And let's say this is the embedding size. Correct? Yeah. So let's say this is the Q. And how does the V look like? The V, how about KT looks like? KT looks like this, right? Right? And this is basically KT. And so Chucky is sleeping at AIT. Okay? Correct. This is Q and KT. Anyone lost? Who understand what I'm talking about? Raise your hand. Okay. Who don't understand what I'm talking about? Okay, great. Right? Then you try to dot them, right? So let me just, okay, I'm screwed. I'm out of space, right? How about I create a new sheet and then we can draw it. Maybe this one can help me? No. Okay. How should I do that? Okay. I don't want to delete anything, but okay. Okay, let me delete this one. So first of all, this guy, what is the shape of this guy? Shape of this guy. Huh? Shape of this guy? 5,3 or 3,5? 5,3, right? This one is 5,3, right? This guy, the shape is 3,5. The first thing you must have in your brain is whenever QKT dot together, what is the final shape? What is the shape? 5,5. Yes, very, very good. You must be very, very familiar with this, that attention, the shape of attention is sequence length, sequence length. Understood? If you cannot understand this, you will never understand my code. You will never understand. But once you understand this, you will see that, Chucky, your code is like so easy to understand. It's simply you understand. You go home and do your exercise. You don't just say, Chucky did not teach, so I will never understand in my life. I watch so many YouTube, I still don't understand. Because you don't understand basic. Did I teach you how to draw? You should know, right? But did I teach you how to draw? Then you tell me what is the dot product, right? So the dot product is a 5 by 5, right? Oh my God. Is this 5 by 5? Yeah. And basically, Chucky is, by the way, today I teach this because someone told me that I need to teach this, is sleeping at AIT, right? And this one is also Chucky is sleeping at AIT, correct? Okay. Now, when you dot them, this guy will try to find attention with this guy, right? And then this guy will be trying to find attention on this guy, and basically pairwise, right? And eventually you'll get this matrix, right? 5 by 5, right? So, by the way, am I too quick? Do you guys understand how did I get this? Who understand how did I get this matrix 5 by 5? Okay. Who don't get how did I get this? Okay, okay. At least you understand that when you dot this guy with this guy, is basically pairwise, right? Pairwise. Now, when you pairwise, what will be high in this matrix? Well, definitely this guy will all be very high, right? Right? This guy will be like 1, right? 1, 1, 1, 1, 1. Like, by the way, I don't know there's no range of numbers, right? Because I did not solve max yet. Actually, here there's a solve max here, right? Correct? But I did not solve. If I did not solve max, then the numbers will be very high. Okay. Which one will have high correlation with Chucky? You think is sleeping at AIT, right? Probably sleeping at AIT, right? Is and at is like very little relationship with Chucky, right? Let's assume we don't need to know because the model will backpropagate and we'll learn, right? The attention. But here we can learn that maybe this guy is high and this guy is high, correct? This will be how it looks in this matrix QK, right? Is, I don't know, okay? I don't know. Sleeping may be related to Chucky and AIT, right? Maybe, by the way, I don't know, okay? I don't know. At may be related to AIT, right? Maybe because it's location. And AIT may be related to Chucky, okay? Maybe do. By the way, I will pause a little bit and let you guys try to absorb it to your blood and soul. Okay? Okay? This is how it looks when you do QKT. This is all bunch of numbers. Higher number mean these two tokens are very related. Low when these two tokens are not related, right? Now, once you get this attention, what do? You dot with V, right? What is V? What is V? V look like this. We also look like this. Understood? We also, QKV are all 5,3, right? So can I ask you, QKTV, what is the shape? Huh? Correct. I'm looking at everyone got it, right? 5,3. you can see, you will get, when you do QKTV, you will get back the same guy, but some numbers will be heightened. That means you want to care about that word. Do you understand? This is the effect of, once you get attention, you multiply back the V, you will know which word you should focus more to answer that. Do you understand? Then you multiply with this one, right? This is the V, right? All right. So can anyone help me? I'm not good in the final shape. My final shape, this is V, V is okay, correct? Five comma three, right? This is the final one, right? Equal to the orange one, right? This is the orange one I'm talking about, right? When you dot this guy with this guy, which cell will be heightened? Which cell will be heightened? Can anyone help me? Basically, you just do this one with this first column, this one with the second column, and this one with the third column, right? Right. This one with the first column, you will get this one, right? This one with the second column, you will get this one, right? Right? This one with the third column, you will get this one, right? So which, this guy, like three of them, right? Three of them with the first column. So this guy would be like three of them, right? Three of them. This guy also three of them with this guy. So three of them. And this guy with this guy, there are three of them. That means that three Chucky is so important, you see? Because three guys are actually paying attention to Chucky. So Chucky embedding, remember this is Chucky is sleeping at ATC, and this three guy is the embedding. Okay? So Chucky will be heightened because Chucky is very, very important. Everyone is paying attention to him. See? So he will be automatically heightened. Right? Now, this is, there's only one guy, right? So you can imagine that this is like 0.1, 0.2, 0.6, right? 0.1, 0, okay, I don't know the number, right? 0.1 times the first guy, 0.6 times the second guy, 0.1, right? Like this, right? You get this number, right? Correct? But because there's only one dark cell, I would just say that it's one importance, okay? And this is one important, right? Again, this guy multiply the second column, you get one. This guy, one. So it makes sense, right? You can see that east is not so important because there's only one guy that pay attention to east, and that is east, right? So east will be reduced importance. This guy also three. This guy two. And this guy, how many? And this is QKV. Understood? It's basically a heightened version of that sentence. It's still, this sentence is still, Chucky is sleeping at AT, correct? It's still this sentence, but this sentence is modified in Chucky in such a way that Chucky has higher magnitude, right? Compared to other guys. So this is QKV. The rest is nothing. When you solve max, you turn all this to 0 to 1, right? You divide it by square root of DK so that it's not too big. That's it. So I want you to all here, whoever study at AIT with me, you should understand this by heart, by soul, and by blood. You should understand that it's nothing. But if you keep on confusing, what is KQ? Chucky say QKV is this, then, but you need to remember like this. Okay, let's take a break and see you guys in a few more minutes. All right, so let's continue this. And I have noticed that this is very messy, but you need to look at the green part, okay? You need to look at the green part. So I'm still talking about the decoder, all right? So as a decoder, once you do this QKVs, you need to do something called mass, right? Mass attention, remember, right? You need to do this mass attention. So how do we do the mass attention? Very simple. You forget what I told you. So mass attention, what is mass attention? You forget what I just told you. You simply, here is everything here will be minus very big value. Okay. Yeah, correct. Okay. So when you do QKT, after you do QKT, you need to set, even though there's attention, you don't allow them to have attention. Understand? By simply setting all this value to be very high, very low, manually set them to like 0.0000 something, okay? Then you can take this and multiply V, okay? Then it will never pay attention to the future words. Then the information will not be used. You cannot allow Chucky to know the future word, right? Because then it will always pay attention to whatever in the future, and then it will cheat, right? So do you guys understand? So in the mass attention, you do QK. Once you do QK, you mask them. How to mask? Set everything, anything future of Chucky, which is sleeping at 80, mask, put them to very low number, okay? And then once you have QKT, you multiply with your V, you will get this, right? But you will not have the same thing as this. You understand? This guy will be changed, right? This guy will be changed, but I will not multiply here for you. Okay. That is the only difference between encoder and decoder. That is, attention is mass. And then once you have that, you pass through some layer norm and some linear layer, right? And then you also, actually, if I'm not wrong, I think this one is added here, right? And you can imagine that Q and this guy can be added because we always keep it to the same shape, 5,3 in this case, right? So this can be 5,3, and this guy also 5,3, right? So they can be always added, right? And then finally, when it's output, it also output 5,3, right? Right. So this is like the transformer architecture. You input 5,3, it will also output 5,3, right? It will always be in the same shape as the input. This is like how transformer works. And if you don't understand why, you just look at each of the operation. Each of the operation keep the same shape. It did not alter the shape at all. The reason why? Simply because if you don't change the shape, you can enjoy the advantage that you can stack this one layer to 12 times, right? You can do this 12 times. You can do this 50 times, right? You can do this so many times. So that's why transformer don't change the shape. How to don't change the shape? Each of the operation will never change the shape. You will always keep the same shape. So now, if I want to do for generation, I just take this 3 guy. I mean, there's a 5 guy, right? And each of these 5 guy has 5 HT, right? H1, H2, H5, right? And then you can send it to something, right? or do whatever you want. What if I want to do for classification? What if I want to use for classification? Now I have 5 edge, right? Which edge I should use to send to the classifier? Do you guys understand my question? I will say it again. When you send this one, output the transformer, you will get 5 guys, right? 5 edge, right? If I want to do classification, I want to know this sentence is positive or negative. I want to know this sentence is who wrote it. This is basically classification task, right? Then which edge I should use? You say last guy, but last guy in this case is AIT. Do you think AIT has the answer? No, right? Then which edge to use? Huh? Mean everything, take mean of it. Okay, that could be a way, right? Take mean of all the edge, right? But the author of GPT, they create a last token called extract. So that you will have the last edge is edge for extract. They will send this guy to the classifier, okay? This is how they do. I will answer your question, yes? Exactly. So whenever you train, whenever you input, you add another token extract. Yes. So now you have, instead of 5 tokens, you have the token number 6. Now Dipali asks, what this guy have? This guy have 3 numbers. In this case, my embedding size is 3. That's why it contains 3 numbers. Where these numbers come from is initialized randomly and randomly propagate. And you train the model that whenever I use this last token, it can classify. So the model will try to learn so such that this token contain all the information of this whole sentence. Automatically, it will be like that. Do you understand? Automatically, the network will know that this guy will contain all the information from all this guy in here, in this layer. And this guy will be able to send to the linear layer to get the answer. The network will automatically know. Yeah. So this is how this extract token comes from. I will pause for a minute. I know I forced this idea to you guys, but I will pause for a minute. And you guys think, seriously, if you read this paper, he only wrote these 2 sentences. By putting an extract token, we allow the model to know that this token summarizes information of the whole sentence. He only write this, and you guys need to think, follow his idea. But I will pause a little minute, and you think. Extract token will be created by user. You remember? By the way, guys, do you remember that actually when you input to the transformer, you also have this token? Do you remember? Who created this? You already code already, right? Who created this? You, right? You are the one that create, right? If you code, you will know you create this, right? No. You also have something called EOS, right? Right? Who create this? You create, right? But how do the model know what is COS? What is EOS? You just learn, and know that EOS, the embedding should look like this. Okay, automatically learn. Similarly, you create a token and append at the very end and say that I don't know whatever. Okay, I create this embedding, I create this token, and whenever I classify, I want to make sure that you only take this token and it can classify. You do it for me. You understand? This is the task that you ask the model to do, right? You may say, Chucky, why you just don't take all the mean, like means POC, just mean all of them? This guy did not do like that. He created an extra token and asked the model, just take this guy and can classify. Okay, so this is the idea. Russia and Deepali asked the same question. What kind of information contains there? Actually, we don't know. but we can intuit that extract actually represent the whole sentence automatically. So for those who still don't understand this, for example, I input the whole sentence, including this token extract. I send to the classifier. I only send this guy, right? And I say, please classify for me something. Automatically, the model will force this guy to be able to classify, correct? The model will force this guy to be able to classify, correct? So what is this guy? We don't know. Deep learning doesn't allow us to know what is inside, but we can intuit or hypothesize that this guy, when you backpropagate many times, this guy actually contains information of the whole sentence automatically. Automatically, yes. Yeah. Everyone, yes. Okay, so Min asked, what is the length requirement of this extract when you append at the end, right? Actually, what is so good about this guy is because we are doing this QK thing, there's no length limit. You can see that, you can see it here. How can extract token know everyone? Because extract will be dotted with everyone, see? So there will be a point in which extract will be super high initially, not initially, in the end, you will know that extract token will contain, everyone must pay attention to extract. This is what we can hypothesize, right? It's because we want it to be able to classify. Okay. So that is the idea. I will pause again. I know I forced this idea to you, and you guys can think. I will give you more minutes. Yeah. What other questions you guys have? Now, I want to continue this. Nowadays, no people have this extract token anymore. Oh, Chucky, you just teach me this extract token, and now you say nobody uses it anymore. I am talking about GPT-1, okay? I'm talking about GPT-1. Finally, now GPT-3, what they do? Anyone can guess. You guess. Anyone can guess. Let's see. Anyone can guess. How they? I'm talking about classification. Okay. Generation, you don't need to add in token, by the way. Okay, because everyone is okay. For classification, if I don't use this extract token, what I use? Can anyone imagine? Please say you will never be wrong because you guys all don't know. Huh? Whole information. Just extract token. No, I already told you, no need extract token anymore. You. Book. Okay. Answer is, you remember this, okay? Actually, no need to remember. This is like so obvious. Actually, not obvious. The CLS token. So if you want to classify anything, you don't need to create this extra token extract. You just take this CLS and put it into classifier and force the model to say that this token should have all the information of this whole sentence. Okay? How? I like this question a lot. How? You don't need to know how because backpropagation, I already answered many times. The backpropagation will take care, right? You just say that. So what we do here is we get a lot of representations, right? We get a representation. Okay, here I use start, right? So let's say this is a representation of the start, right? And this guy is the representation of the next guy. And finally, I have I don't have extract anymore, right? So maybe I have the representation of the last guy, right? Now, if I want to send to the classifier, which one should I send? The GPT-3 guy say that, oh, you just send this guy. Okay, this guy is represented by a start token, whatever, or CLS, whatever is fine. Okay, it doesn't matter what you wrote. Okay, send this to the classifier. When I say classifier, is linear layer. Okay, and then it can predict whether this sentence is positive, negative. It can predict whether this is by which author, right? It can predict whether this is that Thai or English. Basically, any classification task, right? Now, Russia and Deepali have the same question. How does it know, right? Because you force it. You say that, I don't care, okay? I only care that you take this token start. When you send to the classifier, it must answer correctly, correct? There's a loss function, right? That you put. So there's a loss function that you put, and you force it to be always correct, right? And when you force it to be correct, this guy will change, right? This guy will change, right? How this guy change? How this guy can be changed? Well, this guy will be changed, right? This guy will say that, oh, everyone, you should give information to this guy. How to give? Attention. Attention, right? The Q will change, the K will change so that all the attention will be put in here. And this guy will contain all the information necessary for classification, right? But too long to be short, you just understand that backpropagation will force this token to know everything. Yep. So that is the idea. Finally, it comes to the idea that backpropagation is all you need. Okay, it will take care of everything you need. Understood? Understand? Yes. You don't need to know how did you create this token. You randomly initialize and you tell the model, I don't care what. You just give me the answer based on H1. You cannot, you fix your attention, right? You cannot fix, you fix your Q and K, right? You cannot, you fix from here, okay? You fix whatever you want, but H1 should be able to answer my question, right? So that is the way, right? Now, I will pause for, I know I'm a little bit fast. When I get excited, I will be a little bit fast because I know already, right? But I teach this like 5 times. But anyway, I stop a little bit. You guys ask me more questions. Yeah. If not, I move on. And I will move very quickly now because my slide, I have 10 slides I need to finish in 10 minutes. 9? Only 9? Okay, great, 9. Okay, you got it? I hope today I deconstruct everything already and hope you understand. Okay, great. Now, you can now understand why, I hope now after you will understand why there's an extract token. Understand? In the future, do we need this guy? No need. You just use which one? You just use this one. Yes, finish, right? And when you load Huggingface, you can see that many code use the CLS to classify. And this only work for classification, but if you are doing for generation, you don't need to I mean, you don't need to care much because everything is generated like linear, like sequentially anyway, right? So there's no need to care, oh, this architecture cannot do this. Great. Oh, I'm very happy you guys understand. It's not easy, right? It's not easy, but once you understand, trust me, you go and try teach your mom and dad, and then you'll understand my feeling. I will skip, okay? All of it just say that transformer is good. Okay. By the main, I don't want to talk about this much, but basically it's just trying to say that, wow, if you start the architecture from scratch and you train, it's so bad. But if you pre-train a model using general knowledge and you just fine tune for one epoch, it's so damn good. This is called few shot learning. I really want to teach you everything I have in my brain, but I know I cannot. Yeah, feature learning is simply like you load the pre-trained model, and maybe you fine tune using only 5 samples. This is called 5-shot learning. Yeah, and sometimes it works very well. Like only 5 samples. Only 5 samples, it can already do that job. Sometimes, but sometimes it doesn't work. We do many times, it doesn't work. It doesn't work always. But what we're trying to say is that pre-trained model is so cool because you just load the model, you just fine tune a little bit, it works already. Compare you, Chucky, I don't like pre-trained. I will make my model myself and I will fine tune myself, okay? It will take years, okay? So you should always load the pre-trained model and then continue from there. That is what the story about this say, if you're wondering here. Yeah, BERT, I already talked a lot about this. This one I already talked, right? Right, about masking. Here, I just want to say something that when you do BERT, you have to have 3 layers of embeddings, not only position. Usually in BERT, in any transformer, you have two of this, right? Token embeddings and also position embeddings. In BERT, there are 2 objectives. First is predict the mass. But there's also another objective, predict whether next sentence is really the next sentence. I don't know whether it makes sense. It's a binary classification. So whether like, hello, how are you? Did you eat yesterday? This is a 2 sentence followed by one another, right? So in this case, it should be true. But sometimes I can fool the BERT. I say that, hello, how are you? And then I suddenly add another sentence that should not follow this one. Chucky is sleeping at AIT. Here, it should be false, correct? So this is this test. So I can send in my first sentence, my dog is cute, and it should be between CLS and SEP. And then you add another sentence. You randomly pick a sentence from your corpus and then add it, right? If this sentence really follow this guy, it should be, this one should be 1. If it does not follow, it should be 0. So there are 2 tasks that BERT asks you to do. And there's one thing that is so good about my BERT tutorial is I teach you how to have 2 loss together in one model, right? Which is there's a loss of this one and there's a loss. And how do you combine 2 loss? Actually, I have some time. I should show you the code. I know that you will never understand this if I don't show you the code. I will. By the way, anyone has any class after 10:30? Can I teach more, maybe 10 more minutes? At 10:40, okay? Who are tired? Okay. And segment embedding. And so what is segment embedding? 0, 0, 0, 0, 0, and 1, 1. That's it. Okay. The reason why you need segment embedding is because you need to know which sentence is found, right? So there's this guy, and you may not understand where this comes from. It's basically nn.embedding. nn.embedding 2, comma embedding size. Why 2? Because you have 2 sentences. So you want 1 embedding for 0 and 1 embedding for 1. Okay. So this is yeah. Whenever they probably look at me and see my face like, you talk too fast. Okay. Yeah. I will show you the code, okay, today, and then you will understand. I will skip this. Yeah, you guys can read. Okay, these are all the information. When I don't teach, it doesn't mean you should not know, okay? I only teach you like 10 to 20%, like the most critical one, but the rest is also like essential, okay? Yeah, I don't have time. Yeah, I cannot teach you everything. Okay, give me 1 second and then, okay, I will choose 3 slides I want to teach you now. Okay, the first one is sentence bird. So this is a very famous architecture. When you train, you you take 2 sentences that are from the natural language inference data set. So in natural language inference data set, there's a yes, no, and maybe correct, remember? In a natural language inference, where the 2 sentences are really related, right? So you can train a model in which whenever you send to the bird, you get the H, you do some pooling. Pooling is basically just max pool or something. You get the U and V, and then you send U and V and also the vector of U minus V. Send this tree together, it should classify whether it's 0 or 1. Okay? How do you know what does the ground truth come from? The ground truth come from the data set. If the data set say that this 2 sentence is entailment, it should predict 1. If this 2 sentence is contradictory, it should predict 1. So the ground truth come from this data set. Okay? So you train, then you will get a bird that knows how to classify a sentence. Okay? Then you use this as this is during inference. During inference, it's very simple. You just send 2 sentences like Chucky is flying at AIT and Chucky is sleeping at sushi at AIT. You send them, you get the U and V, and then you just dot product. It will give you some score, and you hope that it can be used for understanding whether these 2 sentences are related or not. Okay? So this is like the idea how they train sentence bird. Very cool idea. I pause a little bit. You guys quickly ask me. Oh, you mean this one? This one is cosine similarity, not sigmoid. Cosine. This one is cosine similarity. Basically, just dot product. By the way, do you guys understand how do I train? I mean, first I load the pre-trained model. It's already pre-trained, okay? I already pre-trained, and then I fine-tune it. I fine-tune. So I get this data set called SNLI. So what is in this data set? In this data set, there's many pairs. Like egg is cheap, then the fried rice is cheap. True or false? True or false? If egg is cheap, fried rice is cheap. True or false? I don't know, okay? Let's say true or false? True? Okay, true. All right? And then maybe there's another sentence. Egg is cheap. Chicken is expensive. I don't even know that makes sense. True or false? False, okay? How many you have like this, like 5,000 of this, okay? Right? You have 5,000 of this. Then you load the pre-trained model, you fine-tune this guy. How to fine-tune? You send 2 sentences and put the ground truth according to them and force the model to be able to predict. Okay, so this is the way you fine-tune. Then when you actually use it in inference, You just load the model you already fine-tuned, put it here, right? And then just use it, okay? So this is like a sentence word, like super crazy good one, but super simple. Do you understand? Understand? This guy is important because you guys will all use sentence word. That's why I need to talk. Another guy, I need to teach SimCSE too, right? Because it's in the assignment. Okay. Huh? You mean sentence word, right? This one is in the, okay, no. But this guy is also very good, but I will not teach you very well. But basically, this guy is trying to create embedding. Just like word to vec. And what they do is basically using contrastive learning. So any sentence, by the way, you can do unsupervised manner or supervised. In unsupervised, when I dot myself, it should be high. When I dot with any sentence that is not my self sentence, it should be low. This is the way I train, okay? In a supervised CSE, I can take one sentence and another sentence that is entailment, again, from the natural language inference. They should be high. And any sentence with contradiction, it should be low. And then I train. Finally, I got a model that can create very good embedding. Yep. So that is like the idea of SimCSE. I skip a lot of details, but he actually code from scratch already. You code from scratch, right? Yeah. Maybe you will make a YouTube video, right? Okay, then you guys will better understand. But right? So in BART is an encoder decoder architecture, right? but you can see that in the encoder you can do so many things. You can even remove some items, like Russia say, can we combine mass LM and LM, right? They did not do mass LM, they just delete it. And then they check whether it makes the model better or not. And it does. They found that when you do text infilling, that means that if you ask them to predict this guy too, it's better. Basically combine mass language model and language modeling together, it can be better. Yeah. So that is the idea. Okay. Give me 1 second. I want to show you my code of BERT, and then I will go home. Yeah. By the way, is what I teach very difficult? A little bit, yeah. BERT. Okay. So. Okay, the YouTube. I'm not sharing. Thank you very much. You saved my life. Yeah. Otherwise, people will send email to me. Bye-bye. BERT. So this is BERT, and I load some wiki text, and it's very like basically that short. Because my data set is so short, it doesn't work very well. You guys in the A5, you need to load a bigger data set, okay? Nothing, just split. You can see making vocabs, right? So here I'm just splitting, I'm just creating my own token. You guys ask me where does this code can come from, right? I create by myself. And then I create voter ID. I should not print this. Okay, great. Data loader. You need to have token embedding segment embedding and positional embedding, right? And you also need to do some masking and also some padding. So you can see that, okay, this is not easy to explain, but in a short time. But anyway, basically what I do is first I select two sentences randomly. Randomly, I select two sentences, and then I get all the tokens. I add CRS, and I add, okay? And then I also have segment ID. Segment ID is nothing but 0001111. Okay? And then here, and then here, you say that you only want 15% mass, correct? You only want 15% to be mass. You round, you put an integer because you cannot make a 0 point something masking. But I also put a max one. At least it must be one, okay? If you don't mask anything, it's not okay, right? So at least one. And then I just say that, and I also say that you cannot exceed this one. Then I put a min in front. You understand? I hope this is not difficult, right? If you go from here to here, you will feel that it's not difficult, okay? And then I just select the position to be masked, right? And then how do I select the position? Super easy. I just shuffle the position, and then I just take that many of them to be masked. And then I append them, right? And 10% of them, by the way, what is the output of random? What is the output of random? What is the output of random bracket? What is the output? 0 to 1, right? Right. So I say that if this number is less than 0.1, that means that there's a 10% chance, right? Just simply randomly replace with a random token. 10% of that will be randomly replaced with any token. And then if it's less than 0.9, that means 0.8, right? Then you replace with a mass, correct? But also the rest of the 10%, even you ask them to predict, you don't do anything. See? So this is the key part you need to understand. But by the way, you should not use my code for industry, okay? Here is just, I explain you how to code, okay? And how its inside look like, but when you actually use, you just use. And then you have to pad the position of the tokens and also the input to the max token. And then here is the key, right? If the first sentence +1 is really the next sentence, then it's positive. Okay, and then this is what it needs to predict. It's true. If this guy is not follow the next sentence, then it should be false. And this is the input to the model. The sentence, the segment ID, what token you mask, and the position you mask, and the next sentence prediction. This is the input to the model. Someone asked me, how can I be good at coding? You print step by step. You guys always fancy like, Chucky, how did you code this? I spent 3 days, 4 days to code this because I'm willing to print line by line, slowly. Do you guys have the patience like me? I mean, you should have, right? You should have. If you want to be good like me, like, by the way, I'm not actually good, but I know each of the sentence because I print them all. I don't even know what is this. I print until I understand almost everything. That's why I can teach you guys, right? But if you guys want to be like good, like me, you print everyone. How many days you need? 3 days, 4 days. But it's just one time, right? Just one time. You only do one time. You will forever understand this until you die. Is it worth it? It's super worth it, right? Why you shouldn't do it, right? Why you shouldn't do it? So this is how I learned, and you should learn the same way. So this is what my comment to those who really want to like be crazy at coding. But I will not talk about this too much. But here is like token embedding plus positional embedding plus segment embedding, right? And each of them is basically embedding, nothing else, right? I will not talk about attention mask. You guys can take a look for your A5. I actually explain everything in the video YouTube, but I just want to show you one thing. QKV. Here. No, not here. Oh, by the way, I want to explain this, teach you guys a little bit here. Torch.gather is a very useful function that if the transformer give you all the output, right? You only care about the position that is masked, correct? How do you select those index? There's a function called torch.gather that can just select the output based on this position, okay? And then you can compare this information with the real mask token, just for your information. So here is what I want to show you. Yeah, there are two loss in BERT. The first loss is language modeling. It's simply whether you predict the mask token correctly, correct? And then the next loss is basically whether you correctly predict whether that sentence is the next, and then you add them. When you lost or backward, you will consider two loss together. This is a very, very common way you can create a very powerful architecture, because you balance two loss or three loss or four loss, right? So this is something you must learn from A5. Thank you very much. I will not talk anymore, and I will see you on Wednesday. Wednesday, good news. I will not be the one to teach. Yay! Finally, you don't need to learn from me. He will be the one to teach. Khan, right? Okay, so yeah, please come and enjoy his talk. Thank you very much, and see you next Wednesday. Bye-bye.